Good morning, I'm Manuel Zarzo. We are in Unit 6, Inference into Normal Populations, and then in this video I will explain about the analysis with Statgraphics. We continue with the same example used in the previous video. We have two computer programs, A and B, which are available to search files in a hard disk. So we want to determine which one works faster. So we have 10 files which are searched with each program, and then we measure the time required to find each file. Okay, so these are the values of time recorded. So we have 10 values from one program, 10 values from the other program. Then we compute the sample mean, we compute the sample standard deviation. So the first step is to study data normality, because the formulas that we apply assume normality. So this is the first step. So we can make a normal probability plot with the 10 values from program A, which is this one. So it's more or less, it's not too bad. We can assume normality. And these are the 10 values of the second program on a normal probability plot, which implies that more or less the hypothesis of normality can be accomplished, can be assumed. But it would be better if we could plot the 20 values in just one normal probability plot. How can we do that? Well, so for that we have to think and we have to compute the residuals. Okay. What is the residual? So residual is the part of the observed value due to the variability caused by factors not controlled in the experiment. So this is the definition. Residual is the value observed minus the value estimated by a model. This is a general definition. It's the same for inference, ANOVA, and regression. Okay, remember, it's an important definition. Residual is value observed experimentally minus value estimated by a given model. Usually, that estimation is like an average. Okay, so in this case, so the first observation from program A is 3.4. So this is the value that I have observed. But what is the best estimation? What does it mean? If I measure another value from this program, what is the best prediction that I can give? Well, the best estimation is the average, 3.56. So the residual corresponding to this value, the difference between 3.4 minus the average, and this is negative. Residuals can be positive or negative, and the average of residuals is always 0. So it's not strange to find a negative residual. Now, when I compute the 20 residuals, okay, so 10 from the first program and other 10 residuals for the second program, now I can plot the 20 residuals in a single normal probability plot, which is this one. And so this plot is more powerful to find if we have outliers. In this case, no, because the maximum point fits pretty well to the start line and the minimum value the same, fits pretty well. Also, we can see that the points fit to the line, so we can say that the hypothesis of normality makes sense. It can be assumed. Okay, no outliers are observed. Okay. And here, if we take the median, this value is the median, we can see that the average or the median of all residuals is around 0. Good. What happens if the distribution is positively skewed or right skewed? So here, if I find a curve like that, okay, so some kind of curved distribution, so we should apply transformations. Usually the transformation that work pretty well is the square root, or the fourth root, or even sometimes the logarithmic transformation. Okay, so in Statgraphics, we use this option compared to samples, independent samples. This is the option based on the formulas that I have explained. Okay, then assuming that the null hypothesis is true, so assuming equal variances, the software computes T statistical parameter or computed T statistic. Is the same that I explained in the previous video, and then we have a p-value. Remember, the p-value is always compared with alpha. Usually alpha is 5% or 1%. In this case, we have indicated to the software to work with alpha 5%, as the p-value is bigger, so we cannot reject the null hypothesis. But if we think carefully, this conclusion is a bit strange. Why? Because if we compare, so the conclusion is so that we cannot reject the hypothesis that the mean, okay, so we cannot reject that the means are equal, okay, so this hypothesis makes sense, okay, so the calculations, the statistical calculations say that it makes sense to assume both means as equal, but it is strange because like this value is higher than 2.7, 3.7 higher than 3.2, this is higher than that, this is higher than that. So all values from program A are bigger with the corresponding values of program B. So how is it possible that based on this result we cannot reject the null hypothesis? So for all trials, time for A is bigger than time for B. Okay, and for example, this is the lowest value from A and B, this is the lowest value, and here we have the highest value, okay, and for the same files, okay. So for some reason, this file was more difficult to be found by both programs, and for some reason, this file was faster found, okay. So if we make a scatter plot comparing the time of program B and program A, it makes that we have a correlation, a quite tight correlation. Okay, and that it means that samples are not independent. And this is a very important result. Why? Because we're using the option of independent samples. So we're using a mathematical procedure which does not correspond with the case. Okay, so this is not the best statistical method. Okay, so in this case, just we have checked that samples are not independent based on their correlation, so we're not using the best method. In this case, what we have is that for a set of files, the same file is searched by two programs, another file is searched by two programs. So this is one two-dimensional variable. Okay, so we have 10 files. From every file we measure the time for two programs. But the test that we are carrying out, the test that we are applying is for two one-dimensional variables. So this is one interesting example where we are applying a statistical method which is not the best one for some data, and then this is why the conclusion that we are obtaining seems a bit like strange. Okay, actually what we should do is to apply compare two samples, independent samples. So this option can be done with Statgraphics. I don't have time enough in this subject to explain the theory under this comparison, but what I want to say is that also we obtain a computed t parameter, and the p-value, sorry, this was before what we did, sorry, this is what we did before with independent samples, but the correct method is to compare two samples, paired samples. Paired samples means that we have pairs of data. Pairs of data means that for one file, the time in one program, the time in the other program. For another file, the time in one program, the time in the other program. Actually, we have pairs of values. So the best method is to apply paired samples. So based on this test, which is also based on a t parameter, okay, I don't have time to explain this, but anyway. So here we have a very, very small p-value, which means that the conclusion is to reject the null hypothesis. So look that it is interestingly how in one case the p-value is quite high, so we cannot reject the null hypothesis, but in the other case the p-value is very, very small. So the real conclusion is that we can reject the null hypothesis, which makes sense according to the discussion that I did in the previous slide. So to compare the mean of two characteristics measured in the same individuals, the paired sample comparison is more powerful than the two sample comparison. Okay, the conclusion is that it's very important to choose the right statistical method for every specific type of data. Okay, so an inference. Now let's talk a bit about the statistical language. Sometimes we can say the average is statistically different from 100. It is the same as saying there is enough evidence to say that the population average is not 100. So statistically different means at the population level. If I say the difference between both sample means is statistically significant, it means that the population means are different. So in colloquial language, we can say the price of this laptop is significant. What does it mean? It's a big price. Okay, so it's a colloquial language. The price is significant means big. But in statistics, if I say the differences between these samples are statistically significant, does it mean big differences? Well, the answer is no. Statistically significant means at the population level. So very important. Differences statistically significant don't necessarily imply differences important. Okay? It is just that at the population level, the difference, the mean or the standard deviation is not the same. But actually, in practice, the difference can be small. Because doing the sample size high enough, we can detect a significant any difference of means, though in practice they might be irrelevant. So sometimes we can work with thousands of data. Then when we work with a lot of data, most of the inference tests will lead to reject the hypothesis. But then we have to remember this. So we reject the hypothesis, but in practice the difference might be relatively small. So in practice it cannot be like of much interest. So actually being n tending to infinite is like comparing the size of the two populations. Here I finished this video about analysis with Statgraphics.